Carbon and Climate Panel. Those of you here in person, those of you who join us virtually as well. Our panel tonight is made up of scientists from NASA and NOAA, and you'll be meeting them in just a few minutes. They're right behind me, and they'll be speaking about some new images that we have for what we call Science on a Sphere. Here at the Science Center, you'll see Science on a Sphere beside me, and online you'll be seeing some images from the sphere as well. The sphere is a 6-foot suspended globe that was developed by NOAA to showcase Earth and space science images and data sets. We've had ours here since I think about 2006. There are now about actually more than 100 of these spheres in science centers and museums worldwide, and they're great educational tools for showcasing the latest NOAA and NASA data sets. Over the years, we've developed a number of these data sets for our public and school and education audiences and show them regularly. And a lot of that's been due to help from NASA and NOAA scientists and educators. So because of that, we're pleased to host this event tonight on a very important topic. So to start things off, let me introduce the coordinator for our event, Dr. Stephanie Schollard-Ouz. Stephanie is an earth scientist at NASA's Goddard Space Flight Center, and she's the creator of Climate Bits, which she developed for Science on a Sphere. So please join me in welcoming Stephanie.
Thank you, Jim, and thank you all for coming out on this rainy night, and thanks to the Maryland Science Center for hosting us here. We have a really exciting panel tonight with 4 fantastic experts on different aspects of carbon. As you know, this is a really important time. We have the UN talks, climate talks coming up at the end of the month, and now is your chance to ask questions of carbon scientists. At the end, each one is going to give a brief introduction about their area of expertise on Science on a Sphere, and at the end you'll have a chance to ask questions, and the audience online can send their questions to #AskAScientist, and Frank Niepold here from NOAA is monitoring social media to get those questions. So NASA scientist Claire Parkinson, she's a climatologist, world-renowned climatologist. She couldn't make it tonight, but you're going to hear her voice in this first overview, Climate Bits on carbon dioxide.
Carbon dioxide, or CO2, acts like insulation in the atmosphere, trapping heat leaving the Earth's surface. Because of that, CO2 is called a greenhouse gas, and along with the other greenhouse gases, it keeps our planet from getting too cold, contributing to making the Earth habitable. Since 1958, atmospheric carbon dioxide has been measured at an observatory on the Mauna Loa mountain in Hawaii. The white line shows atmospheric CO2 levels rising and falling at the Mauna Loa Observatory. A fall and rise occurs each year, and the explanation for that lies in the Earth's plants. This image shows plant life measured by satellites. Plants on land are shown in green, while plant life in the ocean is colored green, red, and yellow. Plants take in carbon dioxide from the atmosphere, use it in photosynthesis, and release it when they die or go dormant. The Mauna Loa CO2 curve goes down in the northern hemisphere spring and summer when a vast abundance of plant life is using carbon dioxide in photosynthesis, and the curve goes up in winter when many plants are dormant and no longer photosynthesizing, but animals are still exhaling CO2. While this natural cycle has systematic decreases and increases in CO2 every year, there is also a long-term upward trend drawn as a red line. This gradual change toward more CO2 in the atmosphere in recent decades is in large part caused by humans. We are putting CO2 into the air faster than natural processes can remove it. We do this in many ways, including through our use of coal, oil, and natural gas, and through cement production. Cutting down forests also contributes to more carbon dioxide in the air. Here are measurements of global CO2 with the lowest amounts shaded gray, higher amounts yellow, and highest amounts red. More CO2 is added to the atmosphere in the northern hemisphere where most of us live. Why does it matter that CO2 is increasing? Even though greenhouse gases contribute to making our Earth habitable, too much in the way of greenhouse gases could lead to a level of warming that could have an array of troublesome consequences, including sea level rise and extinctions of species unable to adapt to the changes. Each of us has a carbon footprint. It's the amount of carbon we put into the air through the choices we make about energy consumption, food, and transportation. Each of us could make choices that would help to reduce our individual carbon footprints. For more information, visit climatebits.umd.edu.
And our first panelist is an atmospheric carbon scientist, Emily Wilson from NASA, is going to present her research.
Hi. So as Stephanie said, I'm Emily Wilson. I'm the lab chief of the Laser Remote Sensing Lab at NASA Goddard. And I really enjoyed the last video. I think what you saw was that the highest at Mauna Loa had been recorded was 395 parts per million. And when I went there 2 years ago, they had just noticed that it had reached 400 parts per million, which is kind of a frightening climb, but I guess really since the beginning of the industrial age, we've seen this happening. So my expertise is not looking at the data so much as developing instruments that measure greenhouse gases. So this is a picture of me in the field in Alaska. One of the things we're very concerned about is also methane from thawing permafrost. So right now, estimates of how much carbon there is in the atmosphere is somewhere in the range of 850 gigatons. And most of that's carbon dioxide. Now, the frightening statistic is that there's another, I think if the permafrost thawed, we would bring that number up to 1,400 gigatons. And most of that's methane, and methane's actually a stronger greenhouse gas than carbon dioxide is. So what my vision is, and what a lot of people I'm working with would like to do, is have a global network of ground instruments. Here is little green dots on the globe. And that is where we would like to put our instrument. So just in so much that Keeling really helped policy by measuring CO2 at Mauna Loa I think it was since 1958, we would like to do the same thing and create a long-term climate record with the instruments that we've been developing. And it would also measure carbon dioxide and methane in the atmospheric column as well as water vapor. So the sites that you're looking at in green are AeroNet sites. And AeroNet is a global network of aerosol optical depth instruments. And what we would do is we would connect in with this network and add carbon monitoring to this. I think that's my 5 minutes.
Okay. That's great. Thank you,
Great,
Emily.
thanks.
So before Dwight talks, I'm going to very quickly show, you might be wondering, why does NASA have ground stations to measure things like carbon dioxide? And this is a new satellite called OCO2 that's measuring carbon dioxide in the atmosphere. And this is the first year of OCO2 data. And you can see from this data, this is an experimental satellite run by JPL. You can see in the data that the areas that are black have missing data because the satellite needs sunlight to take its measurements. So in winter or when there are too many clouds, it gets no measurements. So that's a time when we really need ground stations to take the measurements. But one advantage that the satellite has is that it can measure carbon dioxide over the ocean. So that's very quickly, you can see you see how there's high levels of carbon dioxide in the northern hemisphere, and then watch it draw down as the spring bloom starts. It's very dramatic. So with that, Dwight Gledhill is going to now talk about what happens when the CO2 goes into the ocean. Dwight is a NOAA scientist in the Ocean Acidification Program.
Good evening, folks. And Eric McIntosh is going to be flying as my co-pilot on this here, because I don't dare break this. So as Emily described, we have a number of gases emitting from human activities into the atmosphere, and we're all quite familiar with the concepts of climate change and how that carbon dioxide, when it gets up into the atmosphere, it can alter the energy balance of our planet. But I'm the deputy director of NOAA's Ocean Acidification Program. How many people have heard of ocean acidification? That's pretty good. So 15 years ago, none of you would have raised your hand. It's a very rapidly emerging issue, and it's related to the fact that about half of all of the fossil fuel, both fossil fuel and cement production carbon that's been emitted by human activity has actually found its way into the oceans. Okay? This is an illustration showing the carbon flux, the atmospheric flux of CO2 from the atmosphere into the ocean. All of the green areas that we show, this is in the pre-industrial period, all the green areas that you see are areas where carbon is going from the atmosphere and dissolving into the surface oceans. As we project through time, over the next century, you'll see that that flux continues to increase substantially. All right? If we take a look at some areas where there is upwelling, where waters get kicked up along the continental margins, you'll see that where these blue areas are, you'll see these are areas where you still is a source of carbon from the ocean to the atmosphere. So it's not everywhere. But by and large, the entire surface of the ocean is either going to be a sink or a much diminished source of CO2 to the atmosphere. So what happens when the carbon dioxide enters into the surface oceans? You want to show us the next? Okay. So this is a plot. This is Mauna Loa, which we just saw in red. That line there is the atmospheric carbon dioxide concentrations at Mauna Loa. And you can see the seasonal dynamics that were described in the video and that increase, okay, that everyone's familiar with. The blue are observations that are made at ships just off from Hawaii. And that represents the amount of carbon dioxide that's in the water. And you can see it locks on very tightly to the increases in atmospheric CO2. Now, it's very basic chemistry that when carbon dioxide dissolves in water, it will form carbonic acid. This has been known for hundreds of years. There's nothing particularly controversial about basic fundamental chemistry. When you dissolve CO2 in water, any water, it gets a bit complicated. So the CO2 in the water is the blue, and there is a pH decline, hence that carbonic acid. That's pH that we show there in black. And you'll see that it is readily declining, directly observable at these long-term time series. The other thing that changes, which I'm actually going to spend the rest of my 4 or 5 minutes talking about, is the parameter you see in green. In green, that is carbonate ion. And if any of you are familiar with chalk, okay, that's a calcium carbonate mineral. And many marine organisms make their shells and skeletal structures out of basically chalk. And they do that for a very good reason. Seawater is supersaturated with respect to calcium carbonate. So there's a lot of energy that's available for them to actually produce those shells. So if we take a look at how supersaturated the waters were of the world's oceans in the pre-industrial period, this is a map laying out what we call aragonite saturation state. Aragonite's the very common mineral that we find in a lot of shells. Right? The value of 1, shown on this color scale, which is the division between very dark red and orange, that's a point of equilibrium. That's the point where dissolving and precipitating a shell are energetically balanced. Most of the ocean, as you can see, is well above that. It's blue, which means that it is very energetically favorable to precipitate out a shell. And that's where we were in the pre-industrial period. If we take a look at the Arctic Ocean. There we go. I gotta come over here to see it. That's good. You'll see that the only places where dissolution was favored over precipitation in the pre-industrial period was in the very northern latitudes of our oceans. That's important because if we rotate to the equator, and if you take a look at the pteropod, which is just one example of a shelled organism that lives throughout the world's oceans, that produce its shell out of aragonite, what we find is that if you get into waters that are undersaturated, where dissolution occurs, you start to get these very deformed and etched pitted shells, and these organisms tend not to survive. And they happen to be a very important organism at the base of the food cycle. So, in the pre-industrial period, these guys could live pretty much anywhere. So let's go ahead and run us through time. Let's take a look at the northern latitudes first. So here we are in 1950. You'll see that very dark, intense red tends to expand through the northern latitudes quite considerably. And certainly by the year 2030, much of the Arctic Ocean will be corrosive to many shelled organisms. And certainly by the time we get to the year 2100, under a business-as-usual scenario, if you're making your livelihood building shells in the Arctic, you might want to get a different job. Rotate to the Southern Ocean. You'll see that the Southern Ocean is now entirely corrosive to marine pteropods. Now, if we think about what we're up against with the COP21 discussions that will be happening shortly, let's take a look at the COP21 projections. If we can stick to those emission targets we keep the Southern Ocean intact for pteropods. Okay? But not all organisms are sensitive to just dissolution. Sometimes they tend to be sensitive well before we get to that value of 1. Let's take a look at bivalves. So if we take a look at it, this is an oyster larvae. An oyster larvae subjected to conditions where the saturation state is actually 1.4. Below 1.4, we tend to have critical failures in oyster larvae. And some industries are currently being impacted by this already. So if we take a look at that value of 1.4 and look in the world's oceans, where that value of where the water was below 1.4 in the pre-industrial period, we'll find that it only tended to exist in these very high latitudes. And as we start projecting through time, there we are in 1970, 2000. So there we are right now. And as you can see, that area where if you happen to be an oyster larvae, you tend to be in a real crisis situation, certainly by the year 2100. If we look at the United States, even within the Gulf of Maine and along the entire Pacific Northwest, all the way down through California, those waters will be undersaturated, or at least they will be below that critical threshold of 1.4. So let's see what COP21 buys us. COP21 buys us the Gulf of Maine. It buys us much of the Pacific Northwest. Okay? Now, if you're a coral reef, we look at a value of about 3.0. Coral reefs do not exist in waters where oceanic waters tend to be below 3.0 because they need to build faster than all the other processes that break them down move. So there's a balancing act. And in order for them to calcify fast enough, they have to be in waters that are hypersaturated with respect to aragonite. Coral reefs are plotted in white here on this plot, and the red represents waters where saturation states are below 3.0. And in the pre-industrial periods, there aren't any coral reefs in the Southern Ocean, no surprise, and they're certainly not at high latitudes. They tend to keep below about 30 degrees latitudes around the world. Now, if we project forward in time, by about 2065, there will be no places in the world's oceans that will be conducive to coral reef building, okay? With the exception of maybe the Red Sea, which I don't think there's a lot of reefs there. But what does COP21 buy us? I'm totally out of time, aren't I? COP21 buys us much of those regions for coral reefs again. So let's go ahead to the very last slide. I think last slide. I just want to point out, there are things that we can do that we're doing right now. And if we have the information on hand, okay, we have observing systems in place where we're monitoring the chemistry, and when we detect corrosive events, we can inform industries like aquaculture industries where they can modify their activities such that they can shut off their intakes when there's a corrosive event, and they can prove quite successful if they have the right information at hand.
Thank you, Dwight. So Dwight has more data sets that he may show you later on with questions. We have another oceanographer now, Jeremy Wardell from NASA, is going to talk about ocean ecology.
Good evening, everybody. Okay, let's figure this out here. All right, so what we know is that the Earth is warming and that CO2 levels are rising in the atmosphere. What we haven't talked about too much yet tonight is how land and oceans are actually doing us a huge favor. They're taking a chunk of this away. And that's all this cartoon is intended to represent. The top part of it is you see what's adding things, their sources. The bottom part, land, ocean, and atmosphere, are what we call the sinks. And you can see that land and ocean kind of take turns at who does more. But I'm an oceanographer, so I'm going to sell you on why oceans are awesome. And I'm going to spend the remaining 6 minutes I have convincing you that you should think the oceans are awesome as well. So, and really in practice, just to describe this whole process. The driver of the process are phytoplankton. And whether you know it or not, every single person in this room is a huge fan of phytoplankton, even if you don't know what they are yet. And if you don't believe me, ask yourself 2 questions. Do you like breathing? Do you like eating? If the answer to either one of those is yes, you are a huge fan of phytoplankton. Like land plants, they come in all shapes and sizes. They thrive under certain conditions better than others, so they have geographical preferences where they grow best. They form the base of the food chain. They all have different nutritional values. and they're really, really cool under a microscope too. So this is just a little sample of what they look like. But these are the driving forces behind the ocean's ability to take up carbon dioxide. Well, I'm sorry, to remove carbon dioxide from the system. The science term for this is the biological pump. So remember what I said right away. Phytoplankton operate an awful lot like land plants, even though they're microscopic marine algae. They need carbon dioxide, they need nutrients, they need sunlight, they need happy temperatures to survive. And the food chain operates exactly like you think it might. The little guys get eaten by the bigger guys eat the big guys. They're all pooping the entire time while this is happening. But again, all different shapes and sizes here. And so the little guys tend to not sink very fast, and they might get resuspended up near the surface a lot. But the big guys can sink. And since, like land plants, they use this carbon dioxide and convert it into organic material, they're physically removing CO2 from the system. When they're big enough to sink, they drop to the deepest parts of the ocean, and once they're there, it's gone on the order of hundreds to thousands of years. So, big interest in studying phytoplankton, but ocean covers 70% of the Earth's surface. Some of it is really unpleasant, and you can't simply be on a boat and sample all the water all the time, everywhere, constantly. And that's where satellites come in. That's where NASA comes in. Thing is, as awesome as satellites are, they don't physically take a water sample. They can't grab water and do anything with it. So how does a satellite actually give you a picture of where the microscopic marine algae are? It does it using color. Anybody who stood at the edge of the dock in the Chesapeake Bay and then gone out to Bermuda or somewhere like that knows that the color of the water changes depending on where you are. And it's a really good indicator of what's in the water. So the satellites operate like fancy analog cameras. They measure the intensity of light coming out of the water. The only difference is that they do this one wavelength at a time. And if you know how much blue there is relative to green there is and things like that, you can actually take a really good guess about what's physically in the water. So, what you're looking at behind all of these, this global map, is actually a picture of phytoplankton abundance. And the color bar is intended to be intuitive in that the greens are really high concentrations, like you might see in a pond, and the blues are really, really, really clear. So let's put this bad boy in motion. And what you can start to see over time, if you watch the blues and the greens kind of ebb and flow, is that the Earth is breathing. It's almost like a heartbeat when you put this all together. You can't do this if you don't have a satellite. Field measurements are fantastic, and you don't become an oceanographer without wanting to be on a boat. But this is really remarkable. And one thing I want to point out, just in case you're curious, is you see this black ebbing and flowing at the bottom. For this system to work, you need sunlight, and at some times a year, there just isn't enough sunlight to operate this. So I'd like to end tying this back to some physics of the system, just so that we can maybe later talk a little bit about climate change. Remember, phytoplankton are teeny tiny little guys, and they don't swim well on their own. Some of them do a little bit, but the term plankton actually goes back to a Greek word for wanderer. They kind of get pushed around a little bit. And so what you're looking at here are currents in the ocean, and focus on the Pacific there. What you see moving are the currents. The colors that you're looking at are the temperatures associated with it. So off the coast of South America, a lot of really, really cold nutrient water comes to the surface from the deep. And you can see that it's colder there than it is at where you're looking at now on the western side of the Pacific. But suddenly, this cold water is feeding the phytoplankton population. And you might know that there's an anchovy fishery that's very, very productive on the west coast of South America. Well, the current brings these bad boys all the way across the Pacific, and you can see the water's warming. It hits the east coast of Asia, hits Japan, and it starts bending north. There's a western boundary current there. And as the water travels north, you can see the green swirls up top, it cools, and then something called thermohaline circulation takes place. And that's where the water gets cold and dense, and it starts to sink. If we put the abundance of phytoplankton over that, and this is exactly the same data that you saw in the blue-green palette before. It's just scaled differently in a rainbow kind of sense, because this shows scientists a bigger dynamic range. The little clear parts of the water are blue, and the really, really, really concentrated parts where there's a lot of algae are the greens and the reds. But as we come around to the equator here, you'll notice right where the water is coming up and these cold nutrients are coming to the surface, you start to see the bloom. You start to see phytoplankton thriving. And as you watch it going across the equator, you can see that the bloom starts to move. It varies with season. But now start looking up at the North Pacific there. And this is where the story gets kind of important. You have the cold water with the nutrients moving all the way up there, and now the phytoplankton are really, really productive. They're really, really happy. Those are the big guys. Remember I was saying that water starts to sink too. So now you have a system where big guys that want to sink are in water that wants to sink as well. So the reason I bring this up is twofold. One, this is an awesome image and everybody should see it. It's the second time tonight, and we're really psyched about it. It's mesmerizing. But two, phytoplankton don't control where they grow, where they go. They respond to a physical system. CO2 in the atmosphere is warming the Earth is warming the ocean. Ocean warming, currents change, physical conditions change, the whole system is tied together. So I will end. I think I'm out of time, but I will leave you with this. Every second breath you take, say thank you to your phytoplankton.
Thank you, Jeremy. So our last carbon expert is Peter Griffith from NASA, and he studies land carbon.
Hi, everybody. I lead NASA's Carbon Cycle and Ecosystems Office at Goddard Space Flight Center. I'm very happy to talk with you folks tonight. And now I said I would pull up my own slides. There we go.
Okay, this one's awesome.
There we go.
Oh, you know what? It lost connection with this. Oh, there you go. It's working on the second one.
Okay, so let's see if we got. So, well, it says no data were found. So I can talk without the picture.
It's losing
If you want to see if you can bring up the temperature anomaly. I'll go back to a prop. Anybody know what this is? This is coal. This is the first form of concentrated solar energy that people started using. Why do I call this solar energy? Because this was made by plants, and it contains energy from the sun and CO2 from the atmosphere about 360 million years ago. So about 200 years ago, people, we unshackled ourselves from the young, fast carbon cycle, from the energy of horses and our own muscles, and started utilizing this concentrated energy from the sun. Now, the downside to this concentrated energy is that it's releasing the atmosphere from 350 million years ago into our atmosphere, and it's accumulating. And about 120 years ago, in the 1890s, scientists started realizing that CO2 was a greenhouse gas, and so the first predictions were made way back then that we were going to see the planet warm up. And by about the 1930s or 40s, scientists were saying, you know what? Based on what we know about the way heat moves through the Earth system, we think we're going to see the Arctic warming up first. And sure enough, it's taken many decades for these predictions that were based on basic physics to come about. And if you can bring me, tilt that up just a little bit. Well, no, that's good, but just bring me to January. So this is what's called a temperature anomaly. This is sort of like if your normal temperature is 98.6 and you have a 99.6, you're running a 1 degree anomaly. So this is the planet's deviation in temperature from what was the climatic normal in the middle of the 20th century. And lots of us on the East Coast, you heard over and over again, you know, the winter of 2015 was the coldest winter ever. And what you can see with that, with this view, is that 2015 was cold in this one little part of the northern hemisphere that happens to contain a lot of politicians and a lot of media reverberation chambers. But you can see, you know, most of Canada, Alaska was off the charts hot, and I'm not sure if you can see that that the rest of the northern hemisphere, Siberia, was really running a temperature. So this is warming in the Arctic is something that was predicted, you know, so many decades ago that we're now starting to see. If you will put the next one up. So the heat that's being trapped in the Earth system by the CO2 is transported naturally by wind and ocean currents to the poles. And the Arctic Ocean is an ocean covered with ice, surrounded by continents. And you can think of that as a system. You think of your house as a system. Your house is a system that is surrounded by walls, and it has a roof. If you take the roof off of your house, you have a different system. And what this warming is doing is fundamentally changing the system that is the Arctic Ocean by melting this sea ice. So the yellow line is where the minimum amount of sea ice typically happens in September. Back in the early 1970s, when we first started having satellite measurements of the sea ice cover. And this is stepping through, and you see so that starts in 1987, and you'll see the September minimum getting smaller and smaller. And what that is doing is opening up the ocean to direct sunlight. Instead of being reflected into space by the ice, the heat from the sun is warming the ocean. And that warm ocean is dumping more heat back into the atmosphere as winter approaches. Let me have the next one, please. So this is a composite that is showing several things. It's showing the snow cover. It is showing the vegetation growth. It's a vegetation greenness index that we use to measure plant growth. So there's some red dots there too. So there's also a satellite that has a fire detection product. So as the Arctic is warming, you would see the seasonality of the snow changing. You'd see the seasonality of the greening of the vegetation. And you'll also see the seasonality of the fires changing. These are all of these kinds of seasonal changes are being affected by the warming in the Arctic. As a consequence, there are things like increased summer fires in the northern forests. There is an increase in insect infestation of the northern forests because the insects are not being killed by the cold in the winter. There are impacts on things like the 5 billion birds that fly into the boreal forest every summer to reproduce and then migrate back south again each winter. And because of a consequence of this, we're starting up something called the Arctic Boreal Vulnerability Experiment. So over the next decade, we're going to be focusing on northern North America, basically Alaska and northern Canada, and studying how these ecosystems are changing and how it's affecting the wildlife and the people that live in that area, but also how it's affecting the rest of us. One of the ways I just mentioned is, for instance, is that our ecosystems depend on the birds that are breeding in these northern areas. Another thing, though, was mentioned a little bit earlier, is that the ground in this part of the world is typically frozen all year long. The trees sometimes, 400-year-old tree might be as tall as I am, this big around, and shallow roots that are in just this much soil, and right below that is frozen ground. That frozen ground is full of vegetation that's been frozen for thousands of years. So let me finish this, is that this permafrost has this 100,000-year-old vegetation, carbon frozen in it. As it thaws, microbes eat it up, digest it. It's releasing either CO2 or methane, depending on if the ground is wet or not. Those, of course, are greenhouse gases. So that is something called the permafrost carbon climate feedback. The warming is causing CO2 and methane to be released, and that enters the atmosphere, and that causes still more warming. So that is one of the important things that we're going to be studying during the Arctic Boreal Vulnerability Experiment. You can follow that at NASA_above. And while you're moving
Thank you,
this,
Peter.
I'm going to set this thing on the spot where I wanted it.
So does anybody have any questions? Yes, in the back here.
Yeah, I'd be interested in actually all of yours position on geoengineering as to whatever the specific things that you're studying, whether that you're pro or against, or how you stand on that.
Okay, so geoengineering. There is a National Academy of Science study on this, commissioned by the President and done by Mr. Lincoln's National Academies, that was released earlier this year. So I'm going to say some things that are not just my opinion, but the opinion of the National Academy of Science. So it's not just some random carbon cycle scientist spouting off. But one of the things that with geoengineering that is talked about is making more of the sunlight reflect away. That can be done by creating more clouds over the ocean with like fleets of ships that are spraying water into the air to make clouds. It can be done by injecting sulfate, little tiny pieces of sulfate that would be in the atmosphere that cause clouds to condense, water vapor to condense and clouds to form high in the atmosphere. So as long as every country in the world agreed on what the right temperature was, that could be difficult. And you spend $1 billion or every few months pumping this stuff into the atmosphere, you might be able to reflect some of the light away on a temporary basis. But of course, as soon as you stop doing that, then you get instantly all of the heat trapping potential returned, because the CO2 is still there in the atmosphere. So that's not good. But wait, there's more.
I'm just going to randomly spout out my opinion. No,
I was going to do with the OA part.
right, yeah. So, well, a couple things related to that Academy report. Under those conditions where you reflect the energy away from the planet and you're under a different, you've moved to a totally different regime. In the cases where you could pull carbon dioxide back down to where it once was, you sort of move the climate system back to where it maybe was, a little bit better. In the case of reflecting the energy from the planet, you actually move to a parallel dimension, if you will, where you now have, the energy budget being balanced artificially, but you still live in an environment under very high CO2. And I will say that intervention, as they call it in those reports, does nothing for ocean acidification because the carbon dioxide is still there and it's still being absorbed. But there's a variety of geoengineering things that they looked at. The uncertainties around them are quite large. I think the report did recommend that in some cases they would be part of a portfolio of options. I think the case of whether or not we should do geoengineering is sort of a moot point almost at this point. We've been doing geoengineering for hundreds of years. We live in a very artificial planet. And it's doubtful that you'll be in a population of 12 billion people on this planet and it will be a native environment. It will be an artificial, so geoengineering is likely going to be some part of a portfolio. But it, like you said, if it has a huge economic dependency that it be going on, where are the world's priorities going to go when you hit another economic crash? My guess is they're going to, first thing they're going to be cutting is your energy reflecting systems off the planet. That's going to take a massive cut. So I think in very limited cases it might have some applications. The science about it is really uncertain, and I think we're starting to get to the point where if we're recognizing that it might be part of the portfolio, that we have to start investing in the science that's necessary to understand it much, much better. Right now, our opinions on it, for or against, are largely unfounded in the data. We don't really have the data we need.
Thank you, Dwight. We have an online question. Did Jeremy or Emily want to add to that answer?
I have a story, but it can wait.
Okay.
I mean, it's up to you.
So, well, I guess we'll go to the online question, and you can.
So the question is, with increasing CO2, will dry areas get greener as plants have more CO2 to consume in these dry and hot areas?
I guess I'm supposed to be the land. It's a good question, and part of the answer is actually contained in the question. So plants need CO2 to grow. So to some extent, in fact, we are seeing in some forests a CO2 fertilization effect. With higher amounts of CO2, some of the plants can grow faster. But what else do plants need to grow? The questioner mentions water, light, nutrients, as well as CO2. So if any of water or light or nutrients are limited, then it doesn't matter if you add more CO2. So in dry areas, it's unlikely that adding CO2 is going to do much for the plants because they're limited by the water not being there. Several of the speakers mentioned the service that the biosphere is performing for all of us by taking up CO2 from the atmosphere. So not all, in fact, maybe half of the emissions, total emissions from human activities remain in the atmosphere. The rest are taken up by the land and the oceans. So some of these areas where CO2 fertilization has been occurring are the areas that NASA is monitoring by satellite, because that's one of these uncertainties is how long are the plants going to be helping us out that way, performing this service of taking up some of the garbage that we've been throwing into the atmosphere.
Do you want to answer?
I don't, no, that was just.
Or you could tell your story.
All right, I'm going to tell I don't, no, that was just.
Or you could tell your story.
All right, I'm going to tell a story because it's cool. Back to geoengineering. So we talked before about how phytoplankton have a mechanism just like land plants to take CO2, make it into organic matter, remove it from the system. Thus, you're bringing the whole CO2 system down. Geoengineering. Very famous oceanographer called John Martin, early 80s, had a hypothesis, and he had a really bold statement. I think it was at Woods Hole. Just give me a tanker of iron, and I will give you an ice age. And the idea behind this is there are parts of the ocean that have enough light, enough water, enough CO2, enough nutrients, except for iron. They were limited only by iron. And the idea is you take a tanker out there filled with iron, you mow the lawn in the ocean, drop an iron behind you, you create a bloom of these big fast responders that sink fast, and through this sinking and through the photosynthetic process, it actually removes CO2 from the entire system. That said, great story, getting to the uncertainties.
Yeah.
Mathematical modelers have stepped in and found that the error bars on whether this actually works or not, it runs from 10-year, it's a term called sequestration, it's remove it from the system, runs from 10 years to 1,000 years depending on the model, so doesn't necessarily get it away, but it's an awesome quote, and it's an idea.
There have been some small demonstrations showing that even from space you can see the phytoplankton bloom happen from an iron fertilization. But there's really big ecosystem concerns. What is this going to do to the ecosystem at the surface? What is it going to do to the ecosystem at the bottom of the ocean? All of a sudden, you've got gigatons of organic matter raining down on it, and it's been of enough concern that, in fact, there is a United Nations accord that was signed in 2008 that forbids any commercial application of geoengineering with this iron fertilization because it's considered to be just too risky.
But it's a cool story.
But it's a cool story.
Can I ask a question a little bit more along the methane line? So I know that phytoplankton and other things are taking in CO2, but I think methane, I agree with you, is a huge concern and maybe something that isn't talked about as much. So I know you didn't get as much time because you were first. I was wondering if you could expand upon that a little bit. Are there, what are the bigger concerns with methane, and are there things actually, and I'm not a scientist, my apologies, but bringing methane in and taking care of that as well, or is that kind of an outlier we're not really sure about?
Well, the thing about methane is that, well, first of all, there's a lot less of it in the atmosphere to start. I think it's about 1.8 parts per million compared to CO2 is like 400 parts per million. But what makes methane is a stronger greenhouse gas, and sort of to put it in kind of more digestible terms, it just absorbs more infrared radiation in its hydrogen and carbon bonds than CO2 does. Yeah, without getting into the spectroscopy, I think the big concern we have is the permafrost, how much is stored in the permafrost. And while there are estimates, there are different types of permafrost. And I'm really, as much as I'm a scientist, I'm just learning about permafrost too, because we were funded to go to Alaska to make these measurements. And while I'm interested in carbon, permafrost is not something I knew a lot about, but it depends on, as Peter was saying, it depends on the type of site, what kind of gas is being produced, so whether it's wetter or drier. So one of the things that I know different experiments, including above, and we're funded through the interdisciplinary science program, but what we're trying to figure out is, first of all, how much of methane or CO2 is made as produced at each of the sites, varying with what plant life there is and how damp it is. And then to be able to connect that to satellite imagery so you can get a global estimate. I don't know if that answers your question about why methane is a concern, but from the standpoint of that methane's a stronger greenhouse gas, the concern to me is that, and if there is a lot of methane stored in the permafrost and we're not 100% sure how much, as the global mean temperature is rising, we have more and more methane released, which then, as Peter talked about, the process where it's like a feedback loop. So that creates more warming, and then more is released, and then that's quite frightening.
We have a student here with a question.
Say, hi. I have this question so pretend that everybody stopped all these bad things, and then there is not too much carbon coming to the ocean and air and all over the place. But how should we change like the old carbon that's in the ocean and air.
How long will it take to
Like how
go away?
long? Yeah. How long will it take to go away?
Can I?
Yeah.
Go for it.
Yeah,
Yeah.
that's
I know
great.
this is a hard
Great question. Yeah.
This is a really good question. So I think at the heart of your question, you're asking if we all stop doing what we're doing today, how long would it take to fix the problem? And I think by you're saying what we're doing today is using different, well, how are we producing greenhouse gases? A lot of it's coming from combustion, which I think we all know a little something about. So it's not just your cars, it's also your electricity. It's like, how are we producing this? Well, process burners, how we make our electricity, how we drive our cars, this is all leading to it. The fact that you have a refrigerator. So I don't think, this is a very good question because I don't think anybody really has the answer. If everybody, well, and also I think it would be almost impossible for everybody to stop today using your car. And I think people would be really upset if they had to put down the cell phones and their televisions. If they had to turn those off, I think that would really traumatize a lot of people. But I think you're thinking the right direction, nonetheless. Is it safe to say we don't have an answer of how
There's
long?
some, there.
You have
can-
estimates, okay.
There's some things you could say about it. Go ahead.
Oh, well, I'm
I thought you were.
I was going to give it to you. But
Okay, well,
I will,
I'll
I will
take it.
say that from the ocean acidification perspective, I mean, the oceans have quite the capacity to take up the atmospheric carbon. In fact, at the end of the day, in about 10 or 15,000 years, all this said and done, the oceans will have smoothed this all out for us. But we don't live on a time cycle of 10 to 15,000 years. My children will be very old by then. So the ocean cycles tend to move several thousand years. We looked at the current systems moving around the planet. It takes several thousand years for the world's oceans to actually do a full circulation. If you could grab the world's oceans and give them a good shake, all this would go away. But we can't. And it takes thousands of years to actually work this out through the system. That said, if you could immediately abruptly stop the growth of atmospheric carbon in the atmosphere, you would see, you'd see immediate return in the surface ocean chemistry. In most cases, there will be cases where there's still going to be a very long lag time, where we've got upwelling, where you're actually looking at, the carbon coming up from under the Eisenhower administration is coming up under the coast of California right now. So it'll take a while to work itself through the system, but by and large, much of the surface ocean, if you could magically or stop all of our inputs into the system, would actually.
What about breathing? And what about eating and cows?
Well, there's still, but there are natural processes that serve as sinks. So there's a certain. The question isn't how much. It isn't a question of having zero emissions. It's a question of counting up how much of our sinks that we have, natural sinks that take up carbon, and making sure that we balance those processes. What do you want to speak?
So we're at roughly 400 parts per million in the atmosphere right now. And that's incrementing every year. And you see that in that Mauna Loa record. And remember, it's also going up and down each year. So the biosphere would continue to cycle. Every winter, the CO2 would go up a little bit. And every spring and summer, it would go back down a little bit. But the overall increase would, it would stop getting a little bit extra higher every year if we stopped emissions. Then, at that point, the oceans and the land vegetation would, those sinks that I was talking about, that we're all mentioned, would start to work to gradually remove the CO2 from the atmosphere. It would take a couple of hundred years for the CO2 to get back down to what it was when I was a kid, for instance. We've pumped it up that much. Because that is an elevated CO2 in the atmosphere during that time that the sinks are removing it, it means that there would be global warming that would continue. There would still be extra heat trapped in the Earth system for hundreds of years after your magic Harry Potter wand stopped emissions. So that doesn't mean that it's not beneficial to reduce emissions. It's just that it's not the global warming part of it's not just like an on-off switch. The warming will continue for centuries, even if emissions were completely shut off.
We have a few questions online. Frank?
So another question that came in, with global warming, are scientists seeing a decrease in bird migrations in the winter? And if so, how does this impact ecosystems? We may not have the people to answer this question, but we may.
Nothing about birds.
Yeah,
It's different, not reduced.
So the bird migration thing is an interesting one. And in fact, we have a couple of projects that we funded during this Arctic boreal vulnerability experiment, specifically on birds. So some birds, migration is cued on the light cycle. So it doesn't matter if it's warmer or colder. When the sun starts, when the length of the day gets shorter and shorter, they are going to start their migration, and they will move out of the Arctic and south. Usually not such a big deal. The other direction, though, can be a problem. The bird migrations back to the north are cued on light, not on temperature. Now, if spring has come 2 weeks earlier in the Arctic, which it has already, the insects that many of those birds depend on for food are local in the Arctic, and their life cycle cues on temperature. So with warming, you get what the scientists call a trophic disconnect. So it's a disconnection between the food source that the birds are expecting to find and the life cycle of the things that they're going there to eat. So this is, in fact, one of the ecosystem disruptions that is starting to happen in the northern latitudes. Now, there's other birds, like most of the waterfowl, that don't cue on light. They cue on their migration is cued on temperature. So if you live here in Baltimore and you love to see the migratory ducks and geese and things come through, then they're going to show up here when the good hard freezes happen in like the upper Midwest, and the snow hits there, and there's a good strong cold front. Then all of a sudden the Chesapeake Bay fills up with the birds that have a good sense to come and visit us.
Now I know something about birds.
No, it's just the one.
I was wondering about the implications of the influx of fresh water with the northern melting linked to the idea that the phytoplankton needs to sink. The whole, the two of you putting those two issues back to back, really, I was wondering if you could expand on that, please.
Oh, sure. So freshwater is less dense than salty water. And one of the things that phytoplankton need to be successful is to have a system where the nutrients in the lake intersect with each other. And that could create a system where now the way the water is stratified, which means, where the lighter water is floating above, the heavier water is different. Believe it or not, that can create a very, very strong boundary where something can't sink past it, or something from below the nutrients, sorry, I move my hands when I talk, can't get to the surface. Now, that said, this is all complicated by if there is more freshwater input, chances are it's bringing nutrients with it because it's coming from land. So, all to say, it's a great observation because it's a substantial change. It also changes that whole thermohaline circulation pattern that we see too. So rather than giving you the concrete answer, I'm trying to give you all of the things that are going on and how, when you project this out into a decade or 100 years, we don't actually know how it's all going to work out in the end. So super question.
Yeah, that's an area of very active research in what will happen to this thermohaline circulation. They're looking at that with a lot of models.
So can I just also say, related to the ocean acidification intersection with that fresh water, I talked about how we're losing carbonate ion in terms of its concentration as a result of ocean acidification. So calcium carbonate, I mean, there's two things there. I already talked about carbonate. There's also calcium, right? And it's a concentration of those two quantities that make the water supersaturated. So a dilution effect actually can cause similar phenomenon to ocean acidification because you're diluting the availability of both carbonate and calcium. And we see instances, for example, in the New England areas where there's been an increase in intense precipitation events over the past 30 years. I think it's increased something like 71% over the past 30 years of really high intensity precipitation events. Those are causing these freshwater plumes to extend out and actually create potentially corrosive conditions. And we're also seeing, because of the ice melt in the Arctic, freshening of the Labrador Current, which runs along the Scotian Shelf and into the Gulf of Maine. So it's something we're also looking at from the chemical changes as well.
So one other question, this is more general, that came in was, is this going to be archived in a way that they can watch it and share it with other people beyond today?
Yes, this will be archived on the same channel that you're seeing it on now. On the right-hand side, there's a list of videos that have already been captured, and you'll be able to find it there.
Also addressing your question about the fresh water. So one of these persistent oceans, see that cold spot that's just south of Greenland? So watch that place. It has stayed there for the past several winters.
Is that the cold blob?
That's the cold blob.
Okay.
The cold one.
Okay. And with a, it is potentially a indicator of cold fresh water persisting on the surface of the North Atlantic Ocean as it drains out of the Arctic Ocean. So the Arctic Ocean circulation, the main water coming into it is through the Bering Strait from the Pacific. Main water coming out of the Arctic Ocean comes out between Greenland and Iceland there. And we don't really want to see that part staying cold like that and fresh and fresher because it potentially can push the Gulf Stream. If that cold, fresh water stays on the top instead of sinking down into the depths, it can push the Gulf Stream further south than it currently runs, which ironically or perversely can create cold conditions around the British Isles because the Gulf Stream is no longer bathing that part. This is something that the paleoclimate people, the people who study ancient climates, know has happened in the past, that that fresh water out of the Arctic Ocean has moved those warm currents further south. And that is something that there are sedimentary records of happening at times in the past several million years. So it's not just kind of a fanciful idea. It's something that has happened before.
I have a million more questions.
Should we be more worried about reducing our CO2 emissions, get into our atmosphere and then in turn into the water, or about trying to turn those emissions like the phytoplankton do into natural nutrients? So, and like, which one would be more logical in our day and age where we use like combustion engines and phones almost addictively now? Any thoughts on that?
So I will say that there's a new X Prize that's out. I don't know if any of you have seen it. There's an X Prize to actually turn atmospheric carbon dioxide into a usable commodity. And so there have been folks, some companies I think out in California where they've they're like mining carbon out of the atmosphere and turning it into a usable building product, like a cement product. You know, so if you could find a use, you know, so there's I think it's like a $2 million, or I don't know what it is. It's a pretty, you know, my son was very excited. He brought it to school.
Significant.
So it's quite a significant prize for the X Prize Foundation that you could look up on the internet. And so people are, so is it an either or, you know? Do you stop it's both. You reduce your emissions as best you can. I'm not a Luddite. I love my iPhone. Don't let me forget it. I left it over there. So my sense is we happen to be a planet that happens to be conveniently parked very close to a sun that has more energy than we could possibly ever use. I think there are other options that we have to charge my iPod, and our dependence on extracting that energy from the geological reservoirs, that time is probably hopefully past for us.
There's for the young people and the not as young people in the audience, there's a long-form internet blogger called Wait But Why. I don't know if any of you know Wait But Why. He uses language that's not suitable for children at times, I realize, so you will have to self-police on that end of things. But he's really a very stimulating writer, and he has a series on Elon Musk and and the kind of technological developments that Musk is pursuing through Tesla and SpaceX and all these different things to address the kind of challenge that you were talking about there. I think you're probably old enough to read Wait But Why.
So I have to get back to that blob. I'm just so curious about it. So what I'm wondering about is the phytoplankton you talked about that needs to sink, right?
It doesn't need to sink.
It doesn't need to sink.
No.
What are the implications for that fresh water if it comes into play and that phytoplankton doesn't sink?
It will reduce the rate at which they sink, or it will modify the rate. So there are a couple of factors in play here. You have to, if the...
You want your biological pump back on?
Sure. So first of all, you have to think about the environmental conditions this is creating. It's changing it substantially enough that what grows there might change. You know, everything is competing with each other, and it's possible that what's really good there today is not going to be really competitive there tomorrow because something has changed. It flourishes in a salinity that, you know, is now different. You also have that lens of flesh water where even if you have the same particles, maybe now the boundary between that blob and the deeper water has changed and it physically can't penetrate it, or it just slows down. So again, think of these as passive particles in the water. There's no need for them to sink. It's just that they are heavy enough or not heavy enough to be sinking. And the physics of the entire system influences that in the sense that, you know, think of a pint of half and half. You know, you have a fresh stuff, light stuff floating over dark stuff, and if that situation changes, you know, the physics of the system change. But there's no need to sink. It is what it is. They sink or they don't. But if they don't sink, then they stay in the system in a way where they continue to be grazed upon, and that. So that is.
Oh, I can't see that. Okay.
Well, there's what's called the microbial loop. So some of these smaller particles that don't leave the system, they get trapped in this upper layer. It is almost this different microcosm of what's going on. It's since they aren't physically removed from the system through sinking, whatever is there to be continuously recycled. So it's a process of eating, being eaten by other things, being excreted, bacteria come in. But again, this just changes the whole picture.
But it would mean that you're not exporting the carbon into the deep ocean.
Yeah.
But exactly. In
So
that system, it's trapped in the surface water.
Your biological pump of taking the phytoplankton and putting it down deep in the ocean and out of the fast carbon cycle can change, can slow down. Another thing I think Jeremy touched on is that in the deep ocean, the nutrient levels, the nitrogen and phosphorus, is a lot higher because they've had this rain of particles for thousands of years that's accumulated in the deep ocean. And microbes down in the deep water that don't need light eat up all the organic matter and turn it into usable nutrients, nitrogen and phosphorus. And so there's parts of the ocean where that deep, nutrient-rich water comes up into the parts of the ocean where sunlight penetrates, and you get huge blooms of algae that are enjoying the benefits of all the high nutrients, and of course they need light. So if in areas, if there's a change where, in fact, this is not because of, specifically because of global warming. The El Nino cycle is exactly a situation like that. El Nino, in the basic sloshing of this warm pool back and forth across the Pacific Ocean, has been happening for, I don't know, hundreds of thousands of years. I don't know if the paleoclimate people know how old that is, but essentially the cycle that we're in now, when the hot water is up against the coast of South America, is when it shuts off the upwelling of the cold, nutrient-rich water, and so there's a crash of the ecosystems when these phytoplankton are no longer blooming, and the zooplankton, don't have them to eat, and then the little fish, don't have anything to eat, and then the birds don't have anything to eat. The people who lived for centuries along that coast called this phenomenon the El Nino, because it came often around Christmas time. So it's the child, as in the Christ child, that it was named after. But they would find that that their food sources would disappear on these years when that was happening. And the oceanographers sort of stumbled across that when they were studying the upwelling.
We have a question back here.
Yeah, I was wondering what the current thoughts are about ocean temperature and currents. I know that there were, I mean, I haven't been following it for a while, but I know a while back there were these thoughts about these very sudden shifts in currents, potentially due to ocean temperature.
Well, that's a little bit along the lines of my background. The oceans are warming, and that is affecting the currents, but as far as the long-term impact of shutting down the thermohaline circulation, as we mentioned earlier, that's an area of very active research and modeling, but that is definitely of concern and being looked at. Does anybody else want to add to that?
We talked about that earlier. I mean,
Right.
that's that cold blob.
Yeah, the Gulf Stream.
And
Right, the combination of stratification, the freshening, and then the change in
there is
temperature.
actually, I'll put in a plug, I know this is the NOAA Science on a Sphere, but there are a lot of NASA products that get up on this, and the Science Visualization Studio has a really wonderful sort of three-dimensional view of this thermohaline circulation in the North Atlantic, where you can see how it potentially could change. So Stephanie, you can probably give them the link to that. You probably know the one I'm talking about.
Sure, yeah, I can
Yeah.
add that to the educational resources that are on the page for this, the website. Do you have a question?
In Oregon, we have a dead spot off coast that they say they don't know anything about. We don't seem to have any life in that area. Do you know anything about that area?
A dead zone off the coast of Oregon?
I know enough to know that I shouldn't try to answer that. Some of the OA people I know have been talking about that. I've heard it from Sabine.
Right. So I'm not actually terribly familiar about a complete dead zone. I know that there are hypoxia areas that kick up.
Very low oxygen.
Yeah, well, there's very low oxygen waters that can develop, oftentimes due to high nutrient inputs into the system. We see this not just off of Oregon. We see major hypoxia off of coastal Mississippi area, and Mississippi River discharges into the northern Gulf of Mexico. We get huge hypoxic events. Again, very low oxygen events, and that doesn't kill off all life, but it certainly depletes much of it. We see these in many urbanized estuaries. We see it in Long Island Sound, off of Manhattan, and oftentimes they seem to be attributed to high nutrient inputs into the system. And they do intersect with ocean acidification, because not only do they become very low oxygen environments, which is harmful to many of the organisms there, but they're also, the pH is also very low. They become very acidic as well. So I don't know if I specifically spoke to your issue, but I think that might be it.
Yeah, I teach 8th graders, and I would like to know, when I teach about climate change, what message would you like me to take back to them?
It's real. It's happening. It's serious. The science that our agencies and our collaborators do is really unequivocal in that regard. It is, I'm going to take that old, I'm not a scientist. Well, I am a scientist. I'm not an engineer. And the people who are engineers tell me that there are a lot of different ways to dramatically reduce our emissions without, just putting us all living in caves again. There are technical solutions. I am not an economist, but the economists are pretty much unified that it is better to start now rather than later, that the overall costs are lower if we start reducing emissions sooner. I'm also not a politician, and I do not understand a lot of things that are happening in politics. But I do know that your 8th graders are not very far away from being voters, and that even with my my NASA sticker up, I can encourage people to vote and to talk to their politicians, their political leaders, about how important the problem is.
I had something a little more specific for your 8th graders. And I think when I tell people about the research that I do and the instruments that I build, I think a lot of people don't know what greenhouse gases are, believe it or not. So, I mean, if you, at a minimum, if they knew what carbon dioxide was, what methane was, and what water vapor were, and that they were greenhouse gases, and it'd be nice if they knew where their electricity came from. And you can Google this. This isn't hard for a kid. A kid can figure this out really quickly. And maybe start the conversation about solar and wind and other hydroelectric. If you could just, if they at least were exposed to it, I think that would be a really nice start. And I mean, there are really cool experiments you can do outside with, cheap solar panels, and show them what LED lights are. I mean, conservation can make a huge difference. LED lights can use so much less electricity. High fluorescence,
Even
for
complex,
everything.
much less
They've
than
made such a
compact
huge
fluorescence,
improvement, and LEDs have been around forever. And as soon as they start understanding what LEDs are, that's a really easy segue into how does a laser work, and other interesting things that they might be into. But I would be really happy if your kids knew about that.
So we have time for one last question here.
So in the next year and a half, I would say, people have been saying that there's going to be a massive bleaching that's happening on the coral reefs. Do you have anything to talk or anything to say about this?
I mean,
Yeah.
it's happening.
So,
this year.
yeah, absolutely. We're seeing perhaps the most significant El Nino. I think I heard today it may be the most significant we have on record right now. And during those, when we have those events, we often have very high water temperatures. Back in 1998, we had a similar event where the global ocean temperatures got so high we had a global bleaching event or running the coral reefs. But for those who don't know what bleaching is, so corals are both animal, mineral, and vegetable. They are a small animal that lives inside the skeletal structure, but they depend on a plant inside of them to actually photosynthesize and actually pass nutrients and food along to the animal. That's a coral. When things get too hot, they spit out those plants. They're called zooxanthellae. And they call it bleaching because the corals take on a very, very white look to them. And if they last too long like that, they actually starve and they will die. And so there was an awful lot of coral mortality we had back in 1998. And yes, we're watching it very closely unfold right now. We think this will be a very difficult year for corals globally. And we've had reports coming in right now that many of the reefs are starting bleaching out, which is unfortunate because I'm taking my son to Roatan next month. So, but yeah, it's going to be tough.
Is the NOAA website is Coral Reef Watch?
Yeah, Coral Reef Watch. I used to work at Coral Reef Watch, believe it or not,
So
back in the day.
You can find out like the current info.
If you go to Coral Reef Watch, they've got wonderful number of satellite products that look at where we are right now with reef health.
Well, thank you all very much. Thank you all for coming. We're going to end this now because Maryland Science Center needs to turn off the lights here soon, but we really appreciate you all making it out here on this rainy night. And if you have any other questions, you can still email them and we can respond later electronically.
And if you want a NASA sticker, you can come up and get one.
I can try it.